Look, I'm going to be presenting our investigation of primarily the decay of cosmic ray muons. Thomas just finished presenting the speed. And the goals of this lab were to test relativity, see whether or not its predictions were more accurate to what happens in classical mechanics, and also to determine the mean lifetime of muons. And I'm primarily going to be focusing on the second one, on determining the mean lifetime. So, little background on muons. Muons are elementary particles. They have unit negative charge, that is the same charge as electrons. They have spin 1/2, and they're unstable. Why are we interested in muons? They're unstable. This means that we can use them as clock. If we get a creation time, we get a decay time from muons, and so if we also have a creation time, we can figure out how long the interval is between those two. And it's also the case that special relativity predicts time dilation, and so this would let you test the changes in lengths of time due to things moving quickly. They have a relatively long mean lifetime. 2.2 microseconds might not sound like it's that long. It's short for our scales, but it's one of the longest lifetimes of any fundamental particle. I think the only ones longer than it are the proton, the neutron, the neutrino and antineutrino, and the electron. I think that might be it. And the other particles are much, much shorter. Muons have a naturally abundant source. They're created by interactions of cosmic rays with particles in the upper atmosphere. And they're very high energy. And this is related to that they're penetrating. Because they're more massive than electrons, they're not decelerated as sharply by electromagnetic fields. And also because they're fundamental, I think because they're fundamental particles and not larger things like, say, helium nuclei, they can penetrate through matter very well. And so the muons that are generated in the upper atmosphere can get down to detectors inside buildings. And the last point of why muons is that they provide a contact point between theory and reality. There's the theory of Fermi beta decay lets us predict the mean lifetime if we know the mass, or if we don't know the mass, then we can get the mass out of this theory, but we can't test whether or not the theory is accurate. So here's the basics of what we did. The muons were generated by cosmic rays, about 15 kilometers, that should say 15 kilometers above sea level. And we captured the muons in a block of plastic scintillator. And we recorded the arrival and decay events. And because the curve for radioactive decay is time translation invariant, we can get a mean lifetime out of this, even without having recorded the creation event. So what we expect to get is something like this. We expect an exponential curve, some number of counts, times e to the minus t over tau, where tau is the mean lifetime. This curve is plotted with tau being the theoretical value, which is about 2.2 microseconds. But this is only what it looks like if there's no noise. So first of all, there's going to be Poisson noise. There's also noise due to the scintillator, which I will be coming back to soon. So the experimental setup. This is a diagram of it in the lab notebook. Start with this part. The cosmic rays go through a thick block of plastic scintillator. They get captured by atoms and molecules inside the plastic scintillator, and this, I believe it's the arrival, although it might be the capture that the PMTs, the photo multiplier tubes, detect. And at some point in time, so it comes to rest once it gets captured, and some point later it will decay, and this sets off another event. And these events are above the, I think, the 1 mega electron volt background, and they are also sufficiently similar in energy that the PMTs can detect both of them, or that the same PMT can detect both the arrival and the decay events. So the reason that we have two PMTs is because you will get background noise for a PMT. I think the random processes inside PMTs would cause various signals. So if you have two of them, you can significantly reduce this background noise. And this was the noise that I was talking about in the plot that didn't show up in that plot. So we can ask, what will this noise look like? This noise is called accidentals, when you have a signal that shows up in both of them that isn't actually caused by a muon. And this is equal to the total time of integration, or the total time that you're looking over, capital T, times the product of the rate of events from each of the PMTs times the amount of time that you allowed to go by before you say that two things are no longer coincident. So for us, this would probably be around 200. So we used, I think, around 20 microseconds or so for this, because we want to say that. So sorry, I think we used around 200 nanoseconds for that to capture simultaneous events. If you make the time interval too short, then the differences in how long it takes the signal to travel through the cables will make it so that events that you're actually looking for don't get caught. And this is an approximation that works fairly well for the range that we're looking at these numbers. And if you plot that, you get something that looks like this. For those values, those were the ones that were even in waveguides. But I guess here we actually need counts. And if you look at that plot, those are all basically the same. So when you include 0, it actually looks like this. So what we're looking at for the range of times that we're interested in, up to 10 microseconds, it's basically a flat line. So that's the kind of noise that we're going to probably be getting. We're getting something that's approximately a flat line. And so the next step is that we take the output of the coincidence circuit and we send it into a time to amplitude converter, which lets us measure it takes the time between two signals and it turns it into an amplitude, which is easier for computers to measure. And the reason that we have the delay line is so this kind of signal that we're looking for is we delay the start pulse to happen after the stop pulse and send both pulses there. And the reason is that, so the reason we don't do it the other way is we don't want to just measure the delay. We want to measure the time interval between pulses. But the same signal has both our start pulses and our stop pulses. So we get a slightly shorter measurement because there's a delay that we're missing. But this will give us a pretty accurate measurement of the time between intervals, under some conditions at least. So if arrival time, if the interval between, the amount of time between muons arriving is about the same as the amount of time it takes muons to decay, then your signal picture will look something like this. And it'll look like this if your arrival interval is half the decay time. I don't see a difference between those two pictures. But what we're actually looking at is the arrival interval being much, much greater than the decay time. And now you see that it's clear that the signal you're measuring is a signal arrival to its own decay, and then a large period of time passes before the next signal. And so this method of delaying the stop pulse, delaying the start pulse, and then using the same delayed pulse and undelayed pulse of the same thing into the tap will work fine for measuring muon decay times, because the mean lifetime is about 2.2 microseconds. Rate of arrival is about 2 every 10 seconds or so, and that's many orders of magnitude different. So after they go into the time to amplitude converter, they go into the multi-channel analyzer, which basically just reads signal heights and plots them on the computer for us. So time calibration. The multi-channel analyzer only gives us which channel things come in, and it gives us an approximate time or energy, but it seems to not be terribly good at it. So we used a precise pulse generator to generate a series of pulses with a specific amount of time between each pulse. And we ran that through the setup and measured what channels these pulses fell in. I estimated the errors here very roughly. They look to be very, very much overestimated, where for time I estimated the error to be 5, or to be about 1 in the last decimal place that was shown on the machine, because I didn't think to look up what the actual accuracy was in the guidebook. And for the bin numbers, I estimated it to be an error of 0.5 bins. And so you see that this is an extremely accurate linear fit with approximately 19 bins per nanosecond, which is what we were aiming for. So then we measured muon decays. We set this up to run overnight and left it running for about 17 hours. This is the data we get once you convert the channel numbers to time. And the vertical error bars here are Poisson errors. The horizontal error bars, which I'm not sure if you can see any of them, but they're there, are just from uncertainty. I gave the channel number an uncertainty of 0.5 channels and took the uncertainty in the time calibration. And when you fit this to an exponential plus a constant, which is what we think our data will look like, you get that equation, a reduced chi-squared of 0.65, that's pretty good. And this gives us a mean lifetime of 1.99 plus or minus 0.04. So this is a bit low. The book value is 2.20 with significant figures much further than that. And also, I said before that you can calculate the mass of the muons from this. And so the value that we get for calculating the mass of the muons, according to the equation from Fermi beta decay, we get about 108 megaelectron volts. The book value is about 106 megaelectron volts, both of those per c squared. The sources of error. I think the biggest source of error is that I didn't think to account for the delay time. The delay time, there's this amount of time that gets lost by the fact that we're using the same pulse and just delaying the start pulse. And I didn't account for that in my analysis. I didn't think to account for it until like half an hour ago or so, or a little more than that. So all the times are shorter than they should be. And this matches up with the direction of the value that we have. We have a mean lifetime that is lower than what we expect. It's possible that poor estimation of errors, if I didn't quite estimate all the errors right, I had a bit of trouble with the fact that there were zeros. This could contribute significantly. If you just do this least square, if you do a least squares regression and ignore all the errors, you get a mean lifetime of 2.3, which is way on the other side of what we're looking for. And it's another possible contributing factor is that we might not have gotten enough data to get a good estimate of the accidentals. If you just fit two constant times and the exponential without adding a constant, you get 2.06 plus or minus 0.04 microseconds for the mean lifetime. So you can test relativity with the values that we got. So muons are generated 10 to 15 kilometers above sea level, or so it says the lab guide, by cosmic rays. And other experiments which are cited in the lab guide suggest that the most likely momentum is 1 giga-electron-volt over C. To go 10 to 15 kilometers at this momentum, to us it looks like it takes 30 to 50 microseconds. And this is way longer than the mean lifetime. If you throw away all the special relativity, then as Thomas said before, you get a speed of about 9.5 C, and then it only takes 5 microseconds. But we measured these muons to be going at around C and not at around 10 C. So, right, so clearly we need time dilation to account for this. So another thing we can look at is muon intensity. This is a chart from the lab guide of the intensity of muons at different atmospheric depths. At sea level, it looked to be about 10 to the minus 2 muons per centimeter squared per second per steradian. Without time dilation, it takes 30 microseconds to get to sea level. So if we take mean lifetime to be about 2 microseconds, we're only seeing about 10 to the minus 5% of the muons, which means that there would need to be about 10 to the 5 muons per centimeter squared per second per steradian at 10 kilometers up. And as you see from the chart, which peaks somewhere between 10 to the minus 1 and 1, there are nowhere near the 10 to the 5 necessary muons. So, it's another win for relativity. Thank you.